In this video, we're going to look at another operation that you can perform with vectors, and it's called the dot product. The dot product of two vectors is always a scalar answer. It's never a vector answer. So to find the dot product, you multiply the two first components of the two vectors together, and then you multiply the two second components of the two vectors together, and then you add those two. So here's our first example. We're going to do the dot product of the vector 4, 5 and the vector 2, 3. So you're going to multiply the two first components, which are 4 and 2. We're going to do 4 times 2. And then we're going to add that to the two second components, which are 5 and 3. So we're going to multiply 5 and 3. You do want to follow the order of operations, so multiplication comes first. So if you multiply the first two, you get 8. Multiply the second two, you get 15. And now we add these two together. The dot product is 23. So notice how this is a scalar, a single number answer. It is not a vector answer. All right, next example, the first two components are 2 and 6. So we're going to multiply 2 times 6. Then we're going to multiply our second components, -1 and 12. All right, 2 times 6 gives us 12. And then -1 and 12 gives us -12. We add those two together, we get a dot product of 0. And so getting a dot product of 0 actually does tell us a couple things about that vector, and we'll talk about that in just a second. There's also another important property for dot products that you may want to jot down. When you when you do the dot product of a vector times itself, you get that vector's magnitude squared. So in other words, if I square root both sides, the square root of a vector's dot product is its magnitude. So this will come in handy. It's just another way of finding magnitude, and you'll see how that kind of relates to our normal magnitude formula anyway. We'll use that in just a second. Okay, so we have a few vectors here that we want to perform some operations with. Some normal operations, but also combining the dot product now. So we have vector -1, 3, 2, -4, and 1, -2. So for number 1, I just want to do the dot product of vector u and vector v. All right, so vector u is -1, 3, v is 2, -4. I'm going to take the two first components, that's -1 and 2, and I'm going to multiply those. -1 and 2, and I'm going to add that to the two second components, 3 and -4. All right, multiply these, I get -2. Multiply these, I get -12. And then I add those and I get -14. So the dot product is -14. Okay, for number 2, I have a dot product. Then I also have a vector to multiply by after I get the dot product. So I'm going to do the dot product first. I've actually already found the dot product right here. That is the dot product, -14. So -14 times vector w, 1, -2. Now I distribute. So my new vector is going to be -14, +28. Okay, for number 3, I have a dot product, but before I can dot product these, I do want to multiply vector v by 2 first. Okay, so let's go ahead and write down that new vector. If I take vector v and I multiply by 2, I actually get 4 and -8. So new vector, 4, -8, and I'm going to dot product that with -1, 3. Okay, so now I multiply -1 and 4, and then I'm going to multiply 3 and -8. Okay, multiply -4, multiply -24, and now if I add those, I get -28. So when the dot product is the last operation you perform, your final answer is a scalar. When the dot product is the first operation you perform, and then you do another operation after that, it may not be a scalar answer anymore. Okay, but the dot product itself is a scalar answer. Okay, so for number 4, we're asked to find the magnitude. Now, we've already talked about the magnitude in previous videos, but let's use this formula right here to find the magnitude. So we talked about how it's the square root of the dot product of that vector times itself. So we're doing the square root of w dot w. Okay, so let's go ahead and do w dot w. So we're dot producting 1, negative 2 with itself. So that's going to be 1 times 1 added to negative 2 times negative 2. All right, so we multiply those, we get 1. We multiply those, we get 4. We add those, we get 5. Now we put the square root on all that. So square root, square root, square root of 5 is our answer. We would take the square root if it had a square root, but it doesn't. And so notice how that's very similar to the magnitude formula anyway. The magnitude formula is multiply first component squared, second component squared, which is basically what we're doing there anyway. Okay, so for number 5, we're doing a dot product, but before we do that, we're multiplying each vector by something first. So we're going to do 3 times vector v. Let me go ahead and do that. 3 times 2 would give us a new vector 6. 3 times negative 4 would give us negative 12. Okay, and then we're going to multiply vector w by 2, so that would give us a 2 here, negative 4 there. Okay, now we're ready to do the dot product. First times first would be 6 times 2, and then second times second, negative 12 times negative 4. 6 times 2 is 12. Negative 12 times negative 4 is 48, and you're going to combine those and you get 60. 60 as your answer. Okay, magnitude of vector v would be the square root of v dot v. All right, so that's the square root of 2 times 2, or 2 squared, and negative 4 times negative 4, or negative 4 squared, which is the magnitude formula, however you want to look at it. All right, 2 times 2 is 4. That's going to be 16. So this would become the square root of 20, and 20 does actually branch out. So 20 branches into 4 and 5, and 4 branches into 2 and 2, and you get a pair of 2's. So that would be 2 square root 5 for the magnitude. Okay, so the dot product has some interesting characteristics. It can tell us a few other things about vectors. It can tell us if vectors are orthogonal. So orthogonal kind of means the same thing as parallel. The vectors somewhat form 90-degree angles if they were to cross paths. Okay, so if vectors are orthogonal, their dot product is going to be 0. If vectors are parallel, one vector is a multiple of the other. All right, so looking at these vectors here, we want to figure out if they are parallel or orthogonal. Parallel is pretty easy to spot right off the bat, because if you can look at the vectors and automatically tell that one vector is a multiple of the other, in other words, can I take one vector and multiply by a 2 or multiply by a 3 and automatically get the other vector? That's pretty easy to spot. So sometimes spotting a parallel vector is the first thing you want to look for. And then if you don't notice that, then go to the dot product and see if they're orthogonal. And then if neither one of those works, then they're neither. So let's look at the first one. We've got 2, negative 3, and then 6, 4. When I look at these, I notice right off the bat they're not parallel, because if I wanted to get from 2 to 6, I would need to multiply by 3. but multiplying by 3 would not get me from -3 to 4. So parallel is automatically out. So I'm going to try orthogonal now. I'm going to try the dot product. So I'm going to multiply 2 by 6. And then I'm going to try -3 and 4. Remember, I'm trying to get a product of 0, dot product of 0. So I get 12 here, and I get -12 here. I do get 0 as my dot product. So this pair is orthogonal. Okay, I look at the second example. I notice right off the bat that I could get from -3 to 9 if I multiplied by a -3. If I multiplied this -3 by -3, I could get 9. So is the same thing true for 4? Could I multiply 4 by -3 and also get -12? Yes, I can. So that means these two are parallel. Parallel means if they ran side by side, they would not cross or touch each other. Be careful with parallel because the signs have to work as well. The positive and negative signs have to work as well. Okay, looking at this one. To get from 8 to 4, maybe you don't see it as multiplication, maybe you see it as division. I could divide 8 by 2 and get 4. Could I divide -14 by 2 and get -7? Yes, I could. So if that's confusing you, that you're thinking of it as division, what's another way I could think of that? Dividing by 2 is the same thing as multiplying by 1/2 or -1/2. So yes, I could multiply by -1/2. Or sorry, I would not need a negative. Excuse me, I would not need a negative. I'm looking at this sign here instead. I could multiply by 1/2 and get from 8 to 4. I could multiply by 1/2 and get from -14 to -7. And that means this one is a multiple of that one. Or I could go the other direction. I could start here and say, okay, I can multiply 4 by 2 and get 8. I can multiply -7 by 2 and get -14. So either way, one way or the other, it is a multiple. So this is a parallel pair of vectors. Okay, and the last one. If I look at these from -2 to -10, I could multiply by 5. What about 3? Could I multiply 3 by 5 and get to -15? Almost, but not quite. My signs don't quite match up because here I'm going from a negative to a negative, but with a 3 I'm going from a positive to a negative. So it's very, very close to being parallel, but not quite because the signs don't match. So it is not parallel. So now I want to try orthogonal. I want to try the dot product and see if that works. So let's start with your x components, -2 and -10, and then your y components, 3 and -15. So if I multiply these, I get 20. And if I multiply these, I get -45. Okay, so that gives me -25. That is not equal to 0. So no, these are not orthogonal. So this is neither one, neither parallel nor orthogonal. Okay, and so there's one other good application for the dot product, and this is for finding the angle between two vectors. So if your two vectors start at the origin in the coordinate plane, you can find the angle between them by using this formula right here. The cosine of the angle equals the dot product of the two angles divided by the magnitude of the two angles multiplied. Now this formula, notice in the coordinate plane there's two angles that the vectors can form. They can form this angle here, or they could form this big angle around here. So this formula is set up to give you the one that's less than 180. So it's always going to give you the smaller of the two. Okay, and it is this formula. It's a lot to type in, so you want to be careful that you type it all in correctly and keep 4 decimal places and everything to keep it accurate. Okay, so for the first example, we have the vector 4, 3 and the vector 3, 5. So what I typically do is I find the dot product first and get what goes on the top. So let's find the dot product of u and v. Okay, so we have 4, 3 and 3, 5. I didn't mean to put a dot there. I meant to put a comma. Okay, so that's 4 times 3, so that's going to be 12. And then that's 3 times 5, that's going to be 15. So that's going to be 27 that goes on the top of our fraction. Okay, then I want to find my two magnitudes to figure out what goes on the bottom of my fraction. So let's find the magnitude of u first. So the magnitude, remember, is the square root of the first component squared plus the second component squared. So this is the square root of 16 plus 9. So this is the square root of 25, which is 5. Okay, now I'm going to find the magnitude of v. The magnitude of vector v is the square root of 3 squared plus 5 squared. So that's the square root of 9 plus 25, or the square root of 34. Okay, so now we have everything we need, and it's time to plug it into the formula. So I'm going to go back over here for that. So we have the cosine of equals, the numerator was 27 over 5 square root 34. All right, remember we're trying to find the angle. To find the angle, you have to do an inverse cosine. So to type this in the calculator, you're going to type cosine inverse of all of that, 27 divided by, and you might need an extra set of parentheses right here, 5 square root 34 to close that off and make sure that that square root's included in the denominator. All right, so make sure you're in degree mode. So you have second cosine 27 divided by, I'm going to put an extra set of parentheses just to be safe, 5 square root 34. Close that parenthesis off, then close the entire parenthesis off. And I'm getting 22.2 degrees as my answer, 22.2 degrees. So what you want to do once you get that answer, see if that answer makes sense for your problem. Look at where my two original vectors were. If I was to sketch out a coordinate plane, vector 4, 3 is over here, 1, 2, 3, 4, 1, 2, 3. Over 4, up 3, that's that vector. Okay, and then the vector 3, 5 is going over 3, up 5. That's this vector. Both of my vectors are in quadrant 1, and the angle between is right here. It looks pretty small. So the angle 22.2 looks very realistic for what I'm dealing with right there. So kind of eyeball your vectors, sketch them out if you need to, see if the angle that you get makes sense with the vectors that you're given. Okay, let's try another one. Vector u, 1, -4, vector v, 2, 3. So let's start with the dot product. The dot product of u and v. 1, -4, dot 2, 3. Okay, so I'm going to multiply the 1 and the 2, which is 2. Then I'm going to multiply the -4 and the 3, which is -12. Okay, so that gives me -10, which is what's going to go on the top of my fraction. Okay, now I need to find the magnitudes. So start with the magnitude of u. It's the square root of 1 squared plus -4 squared. It's the square root of 1 plus 16, or the square root of 17. All right, now the magnitude of v. That's the square root of 2 squared plus 3 squared. That's the square root of 4 plus 9, or the square root of 13. Okay, so now I have the two things that go on the bottom of my fraction. I'm ready to put it all together. I have the cosine of theta equals negative 10 on top. Now on the bottom, I can do cosine 17, or sorry, I can do square root 17 times square root 13. Or since those are both square roots, I can go ahead and put that into one square root if I want to. 17 times 13 is 221. I can go ahead and make that square root of 221 if I want to. It'll make typing it in a whole lot easier. So I can just make that the square root of 221 on the bottom. And now I'm ready to do the inverse cosine. So theta is the cosine inverse of negative 10 over square root 221, and type that in the calculator. I already see that it's negative. Remember that the cosine is negative, not in quadrant 1, but in quadrant 2. So I should be getting an angle greater than 90 this time, an obtuse angle. Second cosine, negative 10 divided by the square root of 221. Go outside of the square root, close it off, and I get 132.3. So it is obtuse, 132.3. Okay, let's see if that angle makes sense for our problem. Our first vector was 1, negative 4. 1, negative 4. So that means over 1 and then down 1, 2, 3, 4. So that means this vector right here. Over 1, down 4. Our second vector was 2, 3. Over 2, up 3. Over 2, up 3. That's this vector here. So the angle I was finding was this angle right here. That does look obtuse to me. It does look over 90. So 132.3 looks about right for that angle. Okay, so you can always kind of double check and make sure you're on the right track.